If you were to look at your watch, while falling directly into a black hole, you wouldn't actually notice anything wrong. I mean, the second hand would tick just like it always does.
Right, your heartbeat would feel completely normal to you.
Exactly. But to everyone else in the universe watching from a safe distance, you have just stopped entirely.
Yeah, it's wild.
I mean, to them, you've just become immortal, frozen on the edge of the abyss for the rest of eternity.
It really is the ultimate paradox of astrophysics, isn't it? You are not just talking about falling into a deep pit in space. You are talking about crossing the absolute limit of human comprehension.
Which is terrifying.
It is. It's a place where the physical reality you experience completely fractures from the reality everyone else experiences.
And today, that is exactly what we are exploring. We are looking directly into the absolute unknown.
A very profound journey.
Truly. Our mission for this deep dive is driven by a phenomenal set of notes and research we pulled from Ziko's space stories. We are going to extract the most mind-bending, scientifically gripping facts about the ultimate cosmic one-way trip.
Right, to figure out what is waiting in the dark.
Yeah, and what it physically, temporally, and fundamentally does to you.
Humanity's greatest minds, from Einstein to Hawking, spent their entire lives obsessing over this exact mystery. Because a black hole isn't just a heavy object.
No.
It represents the absolute boundary of our knowledge.
Yeah.
Once you cross that line, every single law of physics we rely on is put to the ultimate test.
Okay, let's unpack this, because if we want to understand the profound reality-breaking secrets that a black hole hides, we first have to deal with the immediate visceral problem of just getting close to one.
Oh, absolutely, the physical toll.
Right, because the universe builds this ultimate physical defense mechanism to keep us from looking inside. This isn't just about cosmic destruction in an abstract mathematical sense.
No, this is highly physical.
Yeah, this is about what happens to your physical body. Before we even get to the mind-melting physics of time, we have to survive gravity.
Which is an incredibly tall order.
Yeah.
But what is highly counterintuitive about this initial descent, and our research today highlights this perfectly, is that your journey might actually start out feeling surprisingly peaceful.
Wait, peaceful. Let's pause there.
Yeah, peaceful.
You are falling toward the most destructive, chaotic force in the known universe. How could any part of that initial drop feel peaceful?
Well, it's because of the fundamental nature of freefall in the vacuum of space. If you were to jump toward a supermassive black hole, in those early stages, you wouldn't feel the gravity crushing you from all sides.
Like you were in a deep-sea submarine or something.
Exactly. Not like that at all. You would just feel weightless, exactly like an astronaut floating on the International Space Station. When there's no air resistance, no wind rushing past your ears.
Oh, wow. So no sound at all.
It would be entirely quiet. You would just be drifting toward the darkness.
A completely silent, weightless drift into a monster. That is, deeply unsettling.
It really is.
It's like floating down a quiet river, entirely unaware that there's a mile-high waterfall just around the bend.
That's a great way to look at it.
Yeah.
Because that peaceful sensation is strictly temporary. As you drift closer to the center, the nature of that gravity changes dramatically.
Okay, so things escalate.
Very quickly. You begin to experience a massive, violently steep gravitational differential.
A gravitational differential. Let's break the mechanics of that down for the listener. What does that actually mean for the person inside the spacesuit?
Right. So
why does gravity suddenly act differently?
It comes down to the inverse square law of gravity. Basically, gravity gets exponentially stronger the closer you get to its source.
Okay, makes sense.
On Earth, this doesn't really affect us. The center of the Earth is roughly 4,000 miles away from you. So the fact that your feet are 5 or 6 feet closer to the center of the Earth than your head is completely irrelevant.
Right, I'm not being pulled apart on my morning walk.
Exactly. The percentage difference in distance is virtually zero, so the gravity feels uniform across your whole body.
But a black hole is different.
Radically different. A black hole's mass is concentrated into an unfathomably tiny point at its absolute center. As you get closer to it, the gravity curve becomes infinitely steep.
Wow.
Imagine you are falling feet first. When you get close enough, the distance between your head and your feet suddenly represents a massive percentage difference relative to the center of the black hole.
Because it's so small.
Right. So the gravity pulling on your feet becomes millions of times stronger, than the gravity pulling on your head.
So it's not just a heavy weight on my shoulders, it's my feet literally accelerating faster than my head.
Yes.
And this triggers that terrifying physical process that astrophysicists have given the rather comical name spaghettiification.
Yes, spaghettiification. It sounds like a joke until you realize the sheer mechanical violence it describes. Extreme tidal forces stretch your body vertically.
While simultaneously squeezing you horizontally, right?
Exactly.
The horizontal squeezing is the part that I think people miss. It reminds me of like the old medieval torture rack, you know?
I would F on it.
Where they tie your hands and feet and crank the wheel to stretch your joints out. But this is far worse.
Worse because of the scale.
Right, because all of the mass of the black hole is at a single microscopic point directly below you. So the gravity isn't just pulling you down, it's pulling your left side and your right side inward toward that exact same center point.
That's spot on. You aren't just being pulled down, you are being funneled into a microscopic point. So your sides are crushed inward while your top and bottom are ripped apart.
But I want to push back on the scale of this. You say it rips us apart, but how far down does this destruction go?
All the way.
I mean, is it just tearing flesh and bone, or is it deeper?
Oh, it goes to the fundamental limits of matter. This is a torture rack scaled down to the subatomic level. The differential in gravity eventually becomes so steep that the force across a single millimeter is immense.
That is insane.
It overcomes the chemical bonds holding your cells together. Then it overcomes the atomic bonds holding your molecules together.
And
finally, the nuclear forces holding your atoms together. You are stretched and squeezed until you are literally turned into a single, long, incredibly thin string of human atoms.
absolute dismantling.
Absolute dismantling.
A single string of subatomic particles that used to be a person. What a tremendously dark visual. And what our notes from Ziko Space Stories make very clear is that this absolute destruction happens before you even cross the threshold.
Yes, well before the center.
You are completely ripped apart before you even make it inside the black hole proper. So going back to my initial reaction, that peaceful start escalates into a violent, fundamental dismantling of reality itself.
It's physics operating at a scale that ordinary matter simply cannot endure.
All right, so physically, you are a string of atoms. You are gone. But for the sake of exploring the deepest secrets of this topic, let's suggest a hypothetical.
Okay, let's hear it.
What if you could survive that physical destruction? Let's say we put you in a theoretical, magical, indestructible spacesuit that entirely prevents spaghettiification.
A magic spacesuit, I like it.
Because doing that moves our conversation from the physical tearing of your body to something even wilder, the actual tearing of time itself.
Because now, in your indestructible suit, you are approaching the true boundary, the event horizon.
Yes, the event horizon, the famous point of no return. Our research highlights this as the exact boundary where the laws of physics, as we casually observe them, break down and become pure madness.
Pure madness is right.
And here's where it gets really interesting, because the way you experience crossing this boundary entirely depends on who is watching.
Exactly.
As we mentioned at the start, there are two terrifyingly different perspectives of this single event.
It is one of the most profoundly counterintuitive concepts in all of astrophysics. It is the ultimate disconnect between subjective experience and objective reality.
Let's look at the subjective experience first, the traveler's perspective.
Yeah.
Our listener in the indestructible suit. Okay.
From your perspective, nothing drastically changes in your perception of time. You would simply dive straight forward into the darkness.
Right. To the traveler, time seems to be ticking exactly as it always has. Your biological clock, your mechanical watch, your thoughts, they all feel completely normal to you.
You just cross the point of no return and plunge into the abyss.
You wouldn't even notice the exact moment you crossed it.
But then we look at the second perspective, the outside observer. Imagine I am safely back on a spaceship, parked at a very safe distance, watching you fall toward the event horizon.
Okay, the observer's view.
I did not see you just fall in and disappear. I see you slow down, drastically. And to understand why, we have to explain the mechanism behind time dilation.
What's fascinating here is why this temporal illusion occurs. It comes down to what Einstein taught us about the relationship between gravity, space, time, and the speed of light.
Right.
The one unbreakable rule in the universe is that the speed of light must remain strictly constant for all observers, no matter what.
It's the universal speed limit. It never changes. Exactly. But massive objects, like black holes, severely warp the fabric of space-time. Imagine space-time like a grid. The immense mass of the black hole bends and stretches that grid deeply.
So the light has a harder time traveling.
Yes, if light has to travel through that severely stretched space, but its speed absolutely cannot change, something else has to give.
Space and time compensate for the gravity.
Precisely. To keep the speed of light constant, time itself has to stretch. Time runs slower in stronger gravitational fields.
So as I get closer to the edge,
As you get closer to the event horizon, the gravity becomes so immense that time, relative to the observer far away on the spaceship, stretches out toward infinity.
let me bring in a mechanism-based analogy here because it helps visualize this. Imagine space-time is like a river flowing toward a massive waterfall, the black hole.
Okay, I like that.
Far away from the waterfall, the river flows slowly. You can swim upstream easily. As you get closer, the water speeds up.
Right, the current gets stronger.
But at the event horizon, the river itself is flowing downward at the exact speed of light. Even if you were a photon swimming upstream at the maximum speed possible in the universe, the speed of light, you are just treading water. You can't make any forward progress.
That is a phenomenal analogy. The space-time river is flowing inward at the speed of light at the event horizon.
But wait, stop. Let me play devil's advocate here.
Sure.
Because this is the part that breaks my brain. If I am on the ship watching you, and I see you slow down until you are completely frozen on the edge of the event horizon,
Right.
and time essentially stops at that boundary for you relative to me, how do you ever actually cross it? Doesn't the freezing imply you never actually make it inside?
That is exactly the paradox that trips people up. You do cross it, but the light revealing that you crossed it can never reach the observer.
Oh, okay.
Let's go back to the river analogy.
Yeah.
As you cross the event horizon, the light bouncing off your suit is trying to swim upstream against a river flowing at the speed of light.
So it's stuck.
It takes exponentially longer and longer for each subsequent photon to fight its way out of that gravity well and reach the observer's eyes.
So it's an optical illusion created by the struggle of the light itself.
Mostly, yes. The light loses an immense amount of energy trying to climb out of that extreme gravity. As a light wave loses energy, it stretches out.
Meaning the color changes.
Yes, the frequency drops.
Yeah.
This is called gravitational redshift. So to the observer, you don't just freeze. The color of your spacesuit slowly shifts to red, then to infrared, then to microwaves.
Wow.
Fading dimmer and dimmer until you just wink out of the visible spectrum entirely.
I am trying to wrap my head around the sheer emotional weirdness of this concept. Let's say it's someone you love watching you from that ship.
Yeah, that's heavy.
To them, you never actually cross the line. They watch you hover there, slowly fading into a static red photograph on the edge of the void. You become a permanent ghost stuck on the edge of the hole forever, a glitch in their reality.
A glitch in their reality is a beautiful way to put it.
Yeah.
Because their reality and your reality have fundamentally diverged. They will watch that haunting painting of your final moment for the rest of their lives. But you are already gone. You have already crossed the threshold.
It is deeply haunting. You are experiencing a one-way ticket into the dark, and they are experiencing a frozen monument to your descent that will never disappear.
It's poetry and physics combined.
Truly. But that leads us directly to the next monumental question. You've fallen past the event horizon in your indestructible suit. You are frozen on the outside, but you are falling on the inside.
The point of no return is behind you.
Where does this one-way plunge actually end?
It takes us to the absolute center of the black hole, the destination for everything that gets swallowed, the singularity.
The singularity. The notes we pulled from Ziko's space stories define the singularity as a point of infinite density.
Yes, infinite density.
It is where all the matter the black hole has ever swallowed, entire stars, planets, cosmic dust, and our hypothetical indestructible traveler is crushed into an infinitely small space.
That's the textbook definition, yes.
But earlier we talked about how spaghettiification breaks matter down. How do we explain the mechanism of infinite density? How can something have the mass of 1 billion suns, but take up 0 space?
It defies our everyday logic, which is exactly why the math stops working.
It breaks.
Completely. It's vital to explain why the math breaks here. In physics, we have 2 master rulebooks. We have general relativity, which is Einstein's rulebook for the very large gravity, planets, stars.
Right.
General relativity requires the fabric of spacetime to be smooth and continuous.
Okay, the physics of the massive and the second rulebook.
Quantum mechanics, the rulebook for the extremely tiny, like atoms, subatomic particles. Quantum mechanics is entirely built on things being discrete, choppy, and existing in probabilistic states.
So they are opposites, essentially.
Pretty much. For 99% of the universe, these 2 rulebooks never have to talk to each other. Planets use relativity, atoms use quantum mechanics.
Ah, I see where this is going. The singularity forces them to talk.
Exactly. The singularity is the mass of entire stars, which requires general relativity crushed down into a space smaller than an atom, which requires quantum mechanics.
So they collide.
It forces the two incompatible rulebooks to exist in the exact same microscopic space. And when physicists try to combine the equations of smooth gravity with the equations of choppy quantum particles at zero volume, the math literally breaks.
Wow.
The equations divide by zero and spit out the answer infinity.
So when physicists say the singularity is a place of infinite density where the laws of physics cease to exist, they aren't necessarily saying the universe actually creates a true infinity.
Right, not necessarily.
They're saying our current tools of human understanding fundamentally shatter when we try to measure this. It is a completely blank spot on the map of human knowledge.
Precisely. It is a massive neon sign in the universe that says we are missing a crucial piece of the puzzle.
So what does this all mean? If the singularity is just the place where our math breaks, our source material brings up some revolutionary modern theories about what that blank spot might actually be.
Some really wild theories.
The theories we're looking at today suggest that the bottom of a black hole might not be a dead end at all.
Right, the concept of an exit door.
Exactly. We found some incredible theoretical physics suggesting that the bottom might actually be a cosmic portal, a wormhole.
The wormhole, yeah.
The theory states that everything swallowed by a black hole isn't just crushed into a literal point of nothingness forever. Instead, the intense gravity funnels that matter through a wormhole, violently spewing it out into another universe or an entirely different timeline.
Like a tunnel.
Yeah, and it does this through a mysterious object called a white hole.
If we connect this to the bigger picture of mathematics, a white hole is the exact mathematical opposite of a black hole.
Meaning what exactly?
Well, Einstein's equations don't technically care which direction time flows. So if a black hole is a region of space where gravity is so strong that nothing can escape, a white hole is a region of space where gravity pushes outward so violently that nothing can enter.
Wait, really? Nothing can go in?
Nothing at all. It only emits matter and light. It's essentially a black hole running in reverse.
Which completely changes the entire narrative. Have we been wrongly looking at black holes as these giant cosmic monsters?
It's a valid question.
Like these ultimate trash cans of the universe that just eat and destroy everything? When in reality, they might actually be more like a cosmic subway tunnel.
A transit system.
Yeah, like a deeply violent, high-speed transit system relocating matter to another universe.
If we connect this to the bigger picture, your subway analogy is profoundly accurate. It challenges our fundamental understanding of destruction. What we perceive as the absolute end of matter, the crushing, terrifying death at the singularity, might just be a radical form of cosmic relocation.
Cosmic relocation, I love that. You aren't destroyed, your atoms are just violently relocated to another timeline.
That's the theory.
But if white holes spew out matter, why haven't we ever seen one in our telescopes?
That is the million-dollar question. Some physicists suggest white holes might be incredibly unstable, existing only for a fraction of a second before collapsing.
That would make them hard to spot.
Exactly. But there's a much grander, more mind-blowing theory out there. Some researchers ask, what if we have seen a white hole?
We have.
What if an entire universe worth of matter suddenly exploding outward from a single, infinitely dense point? Sounds a lot like the Big Bang.
Oh, wow. So you're saying our entire universe might be the inside of a white hole, which is the exit tunnel of a black hole, in some other larger parent universe.
It's a purely mathematical theory, but yes.
That is insane.
It implies a multiverse that is far more interconnected and far stranger than a simple collection of stars and planets, connected by these extreme gravitational tunnels.
So the black hole is the entrance.
The wormhole is the transit tunnel, and the white hole is the explosive exit.
That is truly staggering to think about. But of course, because absolutely nothing can send a message back out of a black hole's event horizon, we can never truly know for sure. Which brings us full circle. We've taken an incredible conceptual journey today.
We really have. We've gone from the violent, physical stretching of spaghettiification, where the immense gravitational gradient pulls your very atomic bonds apart,
to the surreal, reality-breaking time dilation at the event horizon, where gravity stretches time so severely that you freeze as a permanent fading ghost to anyone watching from the outside, even as you fall inward.
down to the incomprehensible singularity, that infinitely dense clash between the massive and the microscopic, where all of our mathematical rulebooks catch fire and burn.
And finally, to the theoretical exit door. The possibility that the bottom of the black hole is a wormhole, a white hole portal spewing matter into entirely new universes, perhaps even birthing them.
It's a journey that proves black holes are not just monsters hiding in the dark.
No, they're much more than that.
They are the ultimate keepers of the universe's deepest secrets. They constantly challenge our basic understanding of reality, of space, and of time itself. Every time we think we understand how the universe operates, a black hole forces us to realize how little we actually know.
It makes you wonder, if you had the chance to look inside a black hole and discover the ultimate truth of the universe, the bridge between the rule books, the subway to another universe, would you take that leap?
It's a heavy question.
Knowing that you could never come back, would the knowledge be worth the plunge? I want to leave you with a final, slightly chilling thought to ponder on that. We talked about how, to an outside observer, your image freezes at the event horizon forever.
Right.
And we talked about how, at the singularity, the very laws of physics and time completely cease to exist. So if time freezes at the horizon and time ceases to exist at the center, does falling into a black hole actually mean you die? Or does it mean, in some deeply bizarre structural way, you achieve a terrifying frozen kind of immortality?
A frozen immortality.
Just a little something to think about the next time you look up at the night sky. Keep staring into the dark. We will catch you on the next deep dive.